Hello my dear PU2 students, welcome to Deeksha Karnataka YouTube channel, and today I am going to discuss a very important chapter of your PU2, which is alternating current, as well as one of the smallest chapter of your PU2, EM waves, combined together so that you don't have to wait for both the chapters coming in a later time. So I have decided why not merge them. Also you should remember that from the chapter alternating current you are going to get one full 5-mark question, and according to the past few years trend as well as the model paper shared by your PU board, the question, a 5-mark question that is supposed to come from this chapter is a numerical question. So what we are going to expect from this chapter. So first we are going to discuss alternating current, and then once it is over we will going to discuss EM waves. Okay. But first, before I continue, I request you please subscribe to our channel, share this video with your friends so that they can also learn and score well in your PU2 exam, right? So this is the guide towards your 95% plus in your PU2 board exam, so don't miss out on this. Now let us look into the blueprint of the chapter. So first of all, 1 marker question are 2, so that means we can expect 1 MCQ as well as 1 fill in the blanks from this chapter. There are no short answer type 2 marker or 3 marker questions from this chapter. Straight away 1 5 marker question, and as I mentioned, we are expecting a numerical question from the previous year trend and as well as the model question paper. So we are going to solve 5 numericals from this chapter. So how the discussion going to happen today? So 15 MCQ questions we are going to discuss. We are also going to discuss 5 fill in the blanks and 5 numerical problems. Very important pattern questions are being discussed in this. So if you watch this, definitely you should be able to answer one of the numerical questions that is going to come in your board exam. Now let us start with MCQs. The resonance frequency of a series LCR circuit remains constant even if there is any variation in the value or values of L, C, both L and R. Option D, R. Now we know that frequency, resonance frequency in case of series LCR circuit is given by 1 upon 2 pi square root of L into C. Right, this is the formula for frequency. So we see that if any one of them, L or C, change, then the value of frequency will change. So only if the value of R is changed, the resonance frequency will remain unchanged. So resonance frequency is independent of resistance. So that is the main question. So if you understand that, then you should be easily be able to answer it, right? So frequency is basically independent of resistance R. Next question, when alternating voltage is applied to a resistor, which of the following statement is wrong? So very important, here they asked you which of the following statement is wrong. That means 3 statements are correct, only one of them is wrong. So be careful for such questions where they ask you which of the following is wrong, which of the following is correct. So be careful on such cases. The average current over a complete cycle is 0. This is a true statement. Average current in a complete cycle is 0. It goes up and down, so it's a sine theta. Average of sine theta is 0. The average voltage over a complete cycle is 0. This is again true statement. Okay. Next, the average power dissipated by the resistor over a complete cycle is 0, but average power dissipated in a resistor is not 0. For inductor and capacitor, average power dissipated is 0, but for resistance it is not 0. So this is a wrong statement. So this is our correct answer. You can check the option D. The phase difference between the voltage and the current is 0. Yes. So in case of only single resistor, the current and voltage both remain in the same phase. In case of inductor, current lags by pi by 2. In case of capacitor, current leads by pi by 2. Okay. So here the average power dissipated in a resistor is not 0. Next question, in a transformer, the windings of the primary and secondary coils are wounded one over another to reduce the energy loss due to flux leakage. So just for your information, in this chapter there is a part called transformer, and in your pre-board there is a high possibility 1, 2 or 3 marker question might come from this power loss in a transformer. Power loss in a transformer is very common type of question, so just prepare it for MCQ as well. So power loss in a transformer, there are 3-4 different types of power loss and how to prevent it. Based on that, we have seen some MCQs coming in your question bank as well as in your previous year paper, so be prepared for such question. Okay, so here what when one coil is wound over another, so that the flux that is coming out of the primary should go completely through the secondary, that's why it is done to reduce the flux leakage. Now next question, in case of alternating voltage applied to a resistor, the current leads the voltage by a phase difference of pi by 2. No. The current lags behind the voltage by a phase angle of pi by 2. No. The current and voltage are in same phase. Yes, this is the correct statement. The current leads the voltage by a phase difference of pi by 4. Again, this is a wrong statement. So the correct statement is, in case of simple resistor, current and voltage both are in same phase. Next question, the average power dissipated in an AC circuit is maximum if AC source is connected. So average power dissipated, power is dissipated only through a resistor. Okay, in an AC circuit the power is dissipated only through a resistor. Inductor and capacitor does not dissipate any power. Average power dissipated in inductor and capacitor are always 0. So that means average power dissipated will be maximum when you are connected across only a resistor, nothing else. So that means when only a pure resistor is connected, the power dissipated is maximum. Next question from your question bank, different devices connected to an AC source are listed in the first column, and different phase relations of electric current with the voltage are listed in the second column. Choose the correct match. So it's a match the following type of question. So resistor, inductor, capacitor, okay, lags behind the voltage by pi by 2, in phase with the voltage, leads the voltage by pi by 2. So we know that in case of resistor they are in phase, so 1 should be matched with Q. Okay, in case of inductor it lags behind the voltage by pi by 2. So this is the for inductor, and capacitor leads the voltage by pi by 2. Okay, so now let's see the answers. 1 is with Q, 2 is with P, 3 with R. So this is the correct answer, option C. So here one thing you have noticed that in this case the matching of capacitor and leads the voltage by pi by 2 is direct match. Okay, generally you do not see it, but it is given in your question bank, so it possibly this kind of question you might expect. Generally we expect cross matching. Okay, so this should be here, this should be here, but somehow it was given in this question. Now let's see next question. The resonance phenomenon is exhibited by a circuit only if the following components are present. So for resonance, again the same formula. Resonance frequency is given by 1 upon 2 pi square root of L into C. So what are the components that we need? We need only L and C. R is optional, so L and C must be there. Okay, R is optional, so L and C both are required for resonance. Next, the relationship between peak value Im of current and RMS value is. So what is the relationship between peak value and RMS value? So IRMS is I peak divided by root 2. So correct answer is option B. Okay, remember IRMS and VRMS. So VRMS is also same formula. VRMS is equals to V peak divided by root 2. Sometime in some cases they will give you what is the peak value. So peak value is root 2 times VRMS. Generally in our society we use 220 volt power supply, right? 220 volt 50 hertz is the domestic power supply. The 220 volt that we use is basically the RMS voltage, okay? The peak voltage is higher than that, okay? That's why it is more dangerous, okay? If there used to be a question in the past, why 220 volt AC is more dangerous than 220 volt DC. First of all, 220 volt AC means the magnitude or the maximum peak value is not 220 volt, but it is 220 root 2, which is equivalent to 311 volt, okay, approximately 311 volt. So this is the reason why AC is more dangerous than DC. Same voltage, if the same voltage is given, AC is more dangerous because whenever we say AC, we mention the RMS value, whereas the peak value is root 2 times more than the RMS value, okay? So this is one thing that you should remember. Now next question. An ideal step-up transformer decreases. Step-up transformer means which increases the voltage, okay? Ideal step-up transformer, if you give say VI input, okay, and if you get VO as output, step-up means VO should be greater than VI. Okay, now the voltage increase does not happen automatically, so it has to sacrifice something. What it sacrifices current. So if IE is the input current, then the input current is more high than the output current. So in a step-up transformer, the quantity that decreases is current. Okay, the quantity that decreases is current. Power remains constant. V into I is power. Okay, V into I is power. So if you increasing V, I has to decrease to keep the power constant. Okay, so when you are increasing the voltage, current decreases. When you are decreasing the voltage, current increases. So when you are transferring power from power station to our home, what happens is that the power when it is being transferred, it was increased to a very high value. So 2000 kilovolt, 2 kilovolt or 5 kilovolt, this kind of the voltage when it is being transferred from the power station to our homes, so that the value of current remains low. Okay, so lower current means lesser energy loss during transmission. We don't want to lose too much power when it is being transferred from the power generator station to our homes, right? So what they do, they initially when the power is transferred from the power station towards the city, for example, if power is being generated say somewhere and it is transferred to Bangalore, so between the station, power station and Bangalore city, the power cable are generally very high voltage, okay, generally transferred by very high tension wire. If you have seen, okay, while traveling along a train, or if you are living in a rural area, you have seen that in the in between the crop fields there are very huge towering structure carrying current. So that is basically high tension wire carrying very high voltage power, but that high voltage is useless when it reaches our home. So that's why every city has a power management system. So first it is reduced inside the city to a lesser value, 440 volts, generally 440 volts. 440 volt power is required in the industry, so that is directly sent over there, and from 440 volts to 220 volt is done by the local transformer which is located nearby your house. So they reduce 440 volts to 220 volt, and then it is transferred to your homes. Okay, so the journey of the current from the power station to your home is not very simple. It has involved lot of steps. Now next part, the input voltage to a pure inductor is V equals to Vm sin omega t. Then the current in the circuit is. So in case of pure inductor, we know that current lags by pi by 2. So if this is sin omega t, then the current will be omega t minus pi by 2. Okay, lags means minus, leads means plus. So current must be lagging by pi by 2. So correct answer is I equals to Im sin omega t minus pi by 2. the input voltage to a pure capacitor is V equals to Vm sin omega t, then the current in the circuit is. So again, in case of pure capacitor, current leads by pi by 2. So leads means plus, so that means the answer will be Im sin omega t plus pi by 2. Okay. Question number 12. In a series LCR circuit, the L and the C are interchanged. The resonance frequency of the circuit will. So again, resonance frequency based question. So we know that resonance frequency is equals to what? 1 upon 2 pi square root of LC. Yes, correct. So F is equal to 1 upon 2 pi square root of LC. So that means if you interchange L and C, will the value change? Only the multiplication order will change. 3 2s are 6, 2 3s are 6. Okay, so does not matter if you interchange their positions as long as the formula is obviously valid. So that means L and C, as long as they are connected in the circuit, then the resonance frequency will remain same. So correct answer is remains same. Next question. The power factor of an AC circuit is 1. Then the phase angle between the voltage and the current is. So power factor of an AC is 1 means it is basically only a resistive circuit, or a circuit is in resonance. Okay, in resonance also the power factor is 1. In case of pure resistor also power factor is 1. That means what? The phase angle between the current and voltage is 0. Okay, cos 0. So power factor is basically given by cos phi. Okay, power factor is given by cos phi and it is given as 1. So that means phi must be equals to 0 degree. This is the phase difference. So phase difference is 0 degrees. Now next, which of the following is not a reason for energy loss in a transformer? Another question based on energy loss. Flux leakage is a energy loss. Eddy currents are also an energy loss. Heating effect also an energy loss. Electrochemical effect has nothing to do with a transformer. It can be there in case of an electrolytic cell, but for a transformer this is not there, so this is a wrong option. What type of material should be used as a core to reduce the hysteresis loss in a transformer? Hysteresis loss is basically if you use a permanent magnet inside the transformer core, the magnetic polarity keeps on flipping every time current changes and it gets heated up. Okay, that is called hysteresis loss. To reduce it, you have to use a soft magnetic material. Example is soft iron. Okay, so any material with low hysteresis loss should be used. So that example is soft iron. Okay, material with high hysteresis loss, example is steel, but we generally use materials with low hysteresis loss, that is soft iron. Okay, so now let us move into the fill in the blanks questions. The principle of working of a transformer is dash. So the principle of working of a transformer is mutual inductance. So mutual inductance must be the correct matching over here. The power factor of an AC circuit containing pure resistor, power factor of a circuit containing only pure resistor is equals to 1. So if you see it, mark it and go on. Okay, 1 is also correct, maximum is also correct. Okay, maybe 1 is matching somewhere else, so that's why they have given maximum. Let's see. A rotating vector used to represent alternating quantities is called rotating vector used to represent an alternating quantities is called phasor. Okay, so a vector which represents the phase angle between voltage and current is used by a term called phasor. The average power dissipated in an AC circuit is dash if the AC source is connected to a pure capacitor. So the average power dissipated in an AC circuit is 0. It is 0. Okay. The current through an ideal inductor is called wattless current. because it is it does not consume any power, so that's why it is called worthless current. Now in this case, maximum and 1 both can be the answer. Okay, 1 is not coming over here anywhere else, so that means 1 could also be the answer over here, because the power factor of an AC containing pure resistor is 1, and that is also a maximum value. So 1 and maximum both are correct for this question. So options, obviously one of the options should be changed anyway, but if you see some cases there should be another question which can have another option. That's why we chose certain values as correct. But anyway, if you see such question, you can mark any one of them, you will get full marks. Now let's move on to numerical questions from this chapter. A series LCR circuit contains a pure inductor of inductance 5 Henry, a capacitor of capacitance 20 microfarad, and resistor of resistance 40 ohm. If the AC source of 200 volt 50 Hz is present in the circuit, find the impedance, also find the resonance frequency of the circuit. Easy question. So first of all, what are all the given? Inductor 5 Henry, capacitance 20 microfarad, and resistance 40 ohm. So we have to calculate the impedance and the resonance frequency. Resonance frequency is easy to calculate. Okay, simple formula. We have seen that formula. First we will calculate the impedance. So what is the formula for impedance? Formula for impedance is Z equals to R square plus XL minus XC whole square. This is the first formula that you should remember from this chapter. Now what is XL? XL is called inductive reactance. XL is called inductive reactance. What is its value? Its value is 2 pi F into L. As simple as that. So what is F here? Frequency of the source, which is given 50 Hz. So 2 into 3.14 into F is 50, L is 5. Okay, so it will be 100, 500. Okay, 50 into 200, 100 into 5, 500, 500 into 3.14, which will be 1500 something. Okay, 1575. Okay, if you take 3.15, then that will be 1575. Okay, this will be 1570. You are allowed to use calculator in your PU board exam, so you can use the simple calculator to calculate the exact value. So 1570 is approximated XL. What is the value of XC? XC value is given by 1 by 2 pi F into C. Okay, this is called capacitive reactance. It is called capacitive reactance, right? Now XC value you have to put, we have to calculate. So here 1 upon 2 pi, frequency is 100, frequency is 50, and I have a tendency of making this as 100 because always 50 into 2 turns out to be 100, right? So that's why I tend to write it first even before calculating. Now in the capacitance is given 20 microfarad. Microfarad means 10 to the power of minus 6. So what I will be doing, I will write this 10 to the power of 6 in the numerator. Why? Because 10 to the power of minus 6 in the division, it will go up anyway and become 10 to the power of 6 in the numerator, right? So this is just a step jump. So what we got, 10 to the power of 6 divided by 2 into 50, 100, 100 into 20 is 2000 into 3.14. Okay, so what is 10 to the power of 6 divided by 2000? So 1, 2, 3 zeros. So 3 zeros we can less. So we get 1000 divided by 6.28. Okay, so 2 into 3.14 is 6.28, and 3 zeros cancelled. So we had 10 to the power of 3. 10 to the power of 3 means 1000. So this will be 6 ones are 6. 6 ones are 6, 40, So 46 approximately 166 ohm. You can calculate exact value so this is the value of XC. Okay, exact value you can calculate using a calculator. As I mentioned, I don't like to use calculator. So what is the value of Z now? So the value of Z will be now equals to square root of R square. R square is, what is the value of R? 40. So 40 square plus, here we have 1570 minus 166 whole square. Okay, so the square is on the whole square of this thing. Okay, now let's calculate. So this will be 40 square plus 1396 1390 sorry, not 13, 1406 1404 1404 whole square. Okay, so 1404 whole square. Okay, so if you calculate, it should come around approximately 1500 ohm. Okay, because this is the most dominating part, this is the lower value part, so it should be close to 1500. Exact value we will see in a while, but before going into that, we have to calculate the resonance frequency. What is resonance frequency? So resonance frequency is given by F equals to 1 upon 2 pi square root of LC. So this will be again 1 into, so see, one problem from this chapter is at times it is difficult to solve the question on your hand. So whenever you are solving it, try to use the calculator at the last step. Don't use the calculator at the beginning, but after you have figured out, okay, in this case and this case, you have to use the calculator at the last stage. Okay, once you have get this value, then here also you have to use the calculator. So calculator use is mandatory to solve question from this chapter. So 2 into 3.14 into square root, and you are only allowed to use simple calculator, not the scientific calculator. So you have to take pi's value as 3.14. Okay, what is L? L is 5, this is 20, and 10 to the power of minus 6 microfarad. So 10 to the power of minus 6. So now what you will get? You will get 520 is 100. 100 into 10 to the power of minus 6. So you get this as 1 by 6.28 into square root of 10 to the power of minus 3. So 10 to the power of minus 3 is something tricky. Okay, because 10 to the power of 4 or minus 4 could have been easier because you could take the square root. Okay, but here you cannot. So it will be 10 to the power of 3 by 2 divided by 6.28. The exact answer will be 16, approximately 16 Hertz. Okay, this turns out to be not 1500 but 1412. This turns out to be 1412. Okay, so 1412 ohm is the correct value here. Using calculator you can get that. Again, using calculator you can also calculate this one. Okay, now let's move on to the next question. An AC source of frequency 50 Hz is connected in series with an inductor of 1 Henry, a capacitor of 90 microfarad and a resistor of 100 ohm. Does the current lead or lags the voltage? Calculate the phase difference between the current and the voltage. So first of all, what is the steps? What are the steps? So you have to calculate XL. And XC. So we will do it step by step. What is XL? 2 pi, frequency is given 50 Hz, and L is given here as 1 Henry. So XL is 100 pi or 314 ohm. Okay, so 314 ohm is the inductive reactance. Now what is capacitive reactance? Capacitive reactance is 1 by 2 pi F into C. So problems may be sometimes you might feel boring, but if you practice few of these cases, then all problems you can solve. You can solve all questions that might come into your exam. Okay, that's why problems are very, very specific. You have to solve few questions from this chapter so that you get confidence and what to do if you see any of the questions. Okay, in future I will also be solving previous year questions, so don't worry about it. So once previous year questions are done, then you will be super confident about what are all the questions that you might face. So 1 by 2 pi Fc, so 1 by 2 pi into F is 50, C is 90 microfarad. So 90 micro means what I said, just 10 to the power of 6. Follow the steps. All steps should be same. 2 into 50 is 100, 100 into 90 is 9000 into 3.14. Okay, so Xc becomes so again 1, 2, 3 zeros are gone, and you get 10 to the power of 6 divided by 9 into 3.14, which will be 27.28 approximately. Okay, 28 approximately, and for simplification let me assume this is equals to 30, almost equals to 30. Okay, I don't want to use calculator, so that's why I am using it. So it will be 10 to the power of 6, 1, 2, 3 zeros cancelled, so we get 10 to the power of 3 divided by 30, or 1000 divided by 30. So 0 cancels and you get 33.33. So 33.33 is Xc. Now here the first question is current leads or lags. So current leads or lags depends upon who is greater. So from here we can see that value of XL is way greater than XC. So XL is greater than XC. So if XL is greater than XC, then we say that this is the majority. So current lags. If you find XC is more, then current would be leading. So current leads or lags depends upon the value of XL, okay, and XC. Mutual value of XL and XC. If they are exactly equal, we get the resonance condition. If XL is greater than XC, then we get current lags. If we get XC is greater, then current is leading. Okay, so here as clear as day, current is lagging. Now what is the phase difference? The formula for phase difference is tan inverse XL minus XC divided by R. Okay, XL minus XC divided by R. So XL value is 314 minus 33.33 divided by 100. If you calculate, it will be turning out to be close to 70 degrees. Now you may not be able to calculate 70 degrees without using a sine cos table, but if you keep it like this, 2.79, tan inverse 2.79, then also you should get the full marks, because 70 degrees is not a common angle, so you should not be able to calculate it without using a calculator. Okay, so if you leave the answer over here, so it will be tan inverse 2.79, then also you should get full marks. Okay, but this is a common problem, so 70 degree maybe you can answer, but without using a sine cos table, this exact value may not be able, you may not be able to calculate, and I don't recommend using sine cos table for just a simple problem. So you just leave it over here and get the angle properly. Okay, so this is the correct answer. You should get full marks. Next, A sinusoidal voltage of RMS value 200 volt and frequency 50 Hz is applied to a series RC circuit in which R is equals to 3 ohm and C equals to 800 microfarad. Calculate impedance of the circuit, the current through the circuit, phase difference between the current and the voltage. So R is given, C is given, and they mention this is only an RC circuit. So no L over here. Easy question, right? 50 Hz is the frequency. So what we will be doing first stage is to calculate XC. Okay, so XC is 1 by 2 pi F into C. So that is equals to 1 by 2 pi into 50, and the value of C is 800 picofarad. Microfarad, sorry. So 800 micro means 10 to the power of minus 6, which turns out to be 10 to the power of 6 in the numerator. Okay, so 10 to the power of 6 divided by 100 pi into 800. Okay, so how many zeros are here? 1, 2, 3, 4. Okay, so 1, 2, 3, 4 zeros are cancelled. So what we got? We got 10 square divided by 8 pi. So that is 100 divided by 8 into 3.14. Okay, so which will be approximately 100 divided by 25. If you multiply these two numbers, 3 8 is 24 and point something, which is very close to 25. So we can take this as 4 ohm. Okay, so the approximate value of the XC is 4 ohm. Okay, now R value is given as 3 ohm. So impedance of the circuit, the normal formula of impedance is equals to square root of R square plus XL minus XC whole square. But is there any XL over here? No, right? So XL is not there. So XL not there means we can simply put it equals to 0. So 0 means what? Minus X's whole square. So minus X's whole square is what? Minus X's whole square is simply X's square. Okay, so when only X, R and C or R and L are there, you can still use the same formula. Only thing, whatever is missing, you put 0 in that place and you will get the impedance. Okay, one formula to rule them all. Okay, one ring to rule them all. Right, so one formula to apply everywhere. R is 3 ohm. Okay, and XC is 4 ohm. So we calculated over here 4. So it is 5 ohm. 3 square plus 4 square is common value, 5 ohm. So impedance is calculated, the current through the circuit. So what is the current? Voltage is given 200 volt, Z is 5 ohm. So current must be equals to the voltage divided by the impedance, which is 200 divided by 5. Okay, so that is 40 ampere. So 40 ampere is the current in the circuit. Phase difference between current and voltage. So phase difference value again XL minus X tan inverse XL minus XC divided by R. Now here again XL is not there and we will not take the negative sign. We will simply take XC by R. Okay, or tan inverse 4 by 3. Now 4 by 3 is again another specific value, which turns out to be 53 degrees. Okay, it is a specific angle, so you can check that. 4 by 3 is 53 degrees, 3 by 4 is 37 degrees. Okay, so these are the standard value, sine 53, sine 37, cos 53, cos 37, tan 53, tan 37. These are the values. They are not, even though they are not coming into the standard table, but this is also a very common value. Those who are preparing for JEE or KCET, they should know these values. Again, if you are not sure, you can skip it and leave it over here. You should get full marks, right? Next question. A resistor of 50 ohm, a pure inductor of 250 millihenry and a capacitor are in series in a circuit containing an AC source of 220 volt 50 Hz. in the circuit, current leads the voltage by 60 degrees. Find the capacitance of the capacitor. So capacitance of the capacitor you have to calculate. So what are the method? We know that the phase difference is given by tan inverse XL minus XC divided by R, right? Or tan phi equals to XL minus XC by R. Now tan phi value is given here 60 degrees, so you will put that. So tan 60 degrees equals to XL minus XC divided by R. Now what is the value of tan 60? Tan 60 is √3. So that is equals to √3. So XL minus XC equals to 1.71 into R is given here as 50 ohm. Okay, so that is equals to approximately 85. Okay, approximately 85. So now we are leaving it over here. We will come back to the same part once we calculated XL. Then we can calculate XC. Okay, so what is the value of XL? XL is 2 pi F into L. Okay, inductive reactance. So 2 pi 50 into L is 250 millihenry. 250 millihenry means 250 into 10 to the power of minus 3. Milli means minus. So 50 into 2 is 100. So 100 pi into 250 into 10 to the power of minus 3. So what we got? 1, 2, 3 zeros, 10 to the power of minus 3. So 1, 2, 3 zeros and minus 10 to the power of minus 3 cancels. So we get 25 pi or 25 into 3.14, which will be 2.378, approximately 78. So this will be approximately 78. So now we will use 78 minus XC equals to 85. Okay, so XC equals to 78 minus 85, which is equals to minus 13. So here what mistake we have made is that here current leads the voltage they have mentioned, but we have taken current lags the voltage. So only one small correction we need to do over here is by calculating, instead of XL minus XC, we do not want this negative sign. Okay, that is the major thing. What we will be doing? We will be doing XC minus XL. Okay, so if XL minus XC is positive, then obviously current is lagging, but here current is leading. Current leading means it will be XC minus XL. Okay, so XC minus XL. So this is one small correction is required, not much, but we will do that. So we get XC minus 78. Also one mistake I made. So XC equals to 85 plus 78. Okay, so what mistake you have to be careful about? If current is leading, then it will be XC minus XL. If current is lagging, it should be XL minus XC. Okay, sign should be, you should be careful about the sign. Now let's see, add them. 150, 163. So 163 is approximate value of XC. So XC value we have calculated. Now we have to do the back calculation to calculate the value of C. So XC equals to 1 by 2 pi F into C. Okay, so C equals to 1 by 2 pi F into XC. So just cross multiplication. So XC and C changes the places. So now put the values. So what we got? C equals to 1 by 2 into 3.14 into F is 50 Hz and the value of XC is 163. So if you calculate, you will get that value as 20, approximately 20 into 10 to the power of minus 6 farad or 20 microfarad. Again, you can use a calculator to calculate this value. Okay, I am not going into the calculation part. Now next, a sinusoidal voltage of peak value 220 volt is applied to a resistor, a series LCR circuit with a resistor of series resistance 5 ohm, a pure inductor of inductance 32 millihenry and a capacitor of capacitance 800 microfarad are connected. Find the resonant frequency, calculate the impedance and power dissipated at resonance. Okay, so first of all, find the resonant frequency. Resonance frequency formula, F equals to 1 by 2 pi square root of L into C. So this formula we are going to use, 1 by 2 pi square root of, what is the value of inductance? Inductance is 32 millihenry. And what is the value of capacitance? 800 microfarad. Okay, so let's see. Into 8. So 32 is 16. 4 into 30. So 32 is equals to 4 into 8, and we are multiplying with 8. Okay, and if you take the square root of this, what we get? Square root of 4 is 2 and 8 into 8 is 8, so this will be 16. Okay, so we get this and this as 16, and what we are left with? We are left with 10 to the power of minus 3, minus 6 and 2 zeros. Okay, so 10 to the power of minus 9 plus 2 minus 7. So this is the what we are left with. Okay, so resonance frequency will be 1 upon 32 pi, 16 into 2 is 32, 10 to the power of minus 7, which will be 10 to the power of minus 3, 0.5 or 7 by 2. 7 by 2. Or it will be 10 to the power of 7 by 2 by 32 pi. So what is 10 to the power of 7 by 2, which is 10 to the power of 3 root 10. Okay, so whenever you see that 10 to the power of value x by 2, okay, and x is an odd number, so first of all you divide it, divide the number, and you suppose you get y.5. okay, which is the odd number, you will always get y.5. so take that y value, put it in the 10 to the power of value. So this is equals to 10 to the power of y root 10. Okay, where x by 2 is equals to y.5. Okay, understood? If you have any doubt regarding this methodology, please mention in the comment below, but don't go anywhere. We have one more chapter coming next, right? So 32 pi, and you can calculate the value of the frequency in this case, but the problem is not done. I will show you the frequency in a while. Okay, again, if you have a calculator, calculate it and let me know the answer in the comment section. Calculate the impedance and power dissipated at resonance. So second part, how to solve it? Do we have to calculate XL, XC and all these things? Actually no, because they mentioned impedance and power at resonance. So what is the meaning of that? At resonance, what happens is that XL and XC are equal. So XL equals to XC at resonance. Right, so that means impedance is just equals to the resistance at resonance. Impedance is equals to resistance, that is equals to 5 ohm. So impedance is 5 ohm. What about the power dissipated? Power dissipated is given by V square upon R, that is 220 square divided by 5. So that is 220 into 220 divided by 5. So we get 4 5s are 20 and 4 5s are another 20. Okay, so you get this is equals to 22 into 22 into 2. So the answer you will get as 4840. 4840. Sorry, I take some help from my answers. Okay, and the resonance frequency will come out to be 10 Hz. You can take the answer, you can check the answer, it will turn out to be 10 Hz. Now let's move into electromagnetic waves, the second chapter. So how many questions we can expect from this chapter? This is the smallest chapter, as I mentioned. We are expecting 1 MCQs as well as 1 2-marker question. So how many questions we are going to discuss? 15 MCQs and only 5 2-markers, so almost there. So just hold on for 10-15 minutes, this should be over. But before I continue, I request you, first of all, please share this video with your friends. Secondly, please join our WhatsApp channel. The link of the WhatsApp channel is given in the description section of this video. There you will get all the updates, all the information regarding your PU2, your KCET, and all the counseling infos in future as well. So the ultraviolet region of the electromagnetic wave spectrum lies between X-ray and visible region, microwave and radio wave region, gamma ray and X-ray region, visible region and microwave region. So if you see that ultra wave, so this is our, suppose this is our spectrum. So it start with first gamma ray, next is X-ray, then is UV ray, then we have visible ray. Visible means the lights that we see, the lights that you are seeing right now, because I am recording in visible region of the wavelength, that's why you are able to see me. If I am recording in UV rays or in the infrared rays, you would not be able to see me, right? So visible after UV is visible, then we have infrared ray, then we have microwaves, and then we have radio waves. Okay, in the radio wave first comes FM and then comes AM. Okay, so now let's see the portion. What is the question? The ultraviolet region. So ultraviolet region is falling between X-ray and visible ray. So it is falling between X-ray and visible region. The expression for displacement current ID is ID equals to epsilon naught d phi E by dt. Remember, it is because of electric field, and electric field is given by epsilon naught, not mu naught. So be careful. ID equals to epsilon naught d phi E by dt. When you are writing the Ampere circuital law, modified Maxwell and Ampere circuital law, that time this term comes over there, because in Ampere's law we have mu naught I. Right, B dot dl equals to mu naught I, so that's why that mu naught comes over here. But in general, the normal expression for displacement current does not have any mu naught. Very common mistake, and this question has repeated multiple times in history, so please be careful about this. Next question, the electromagnetic waves with lowest frequency among the following. So if you remember, we are starting with gamma ray, then X-ray, then UV ray. So whoever starting first has smallest wavelength and highest frequency. Okay, so here they have stated lowest frequency. Lowest frequency means radio waves. Lowest frequency is radio waves. Okay, this has highest frequency, this has lowest frequency. Everything is in between. Next question, the electromagnetic waves suitable for radar system used in aircraft navigation are. So in radar system we generally use microwaves. Microwaves is very common, which is used in the radar system. So microwaves is the correct answer. Next, X-rays, microwaves and gamma rays traveling in vacuum have same velocity but different wavelength, same wavelength but different velocity, same velocity and same frequency, same frequency and different frequency. I think this should be different wavelength. Okay, so first of all, let us understand X-ray, microwaves and gamma rays, they are all electromagnetic waves. All electromagnetic waves travel with the speed of light, which is equals to 3 into 10 to the power of 8 meter per second. It does not matter whether it is a visible ray, whether it is a gamma ray, whether it is a X-ray, all rays travel with the speed of light. Okay, but X-ray, gamma ray, microwaves, all other rays, they have different frequencies and different wavelength. Frequencies and wavelengths are different, but speed is same. So same velocity but different wavelength. Same velocity but different wavelength. Same velocity, different frequency could be also correct answer. Okay, but here same velocity, same frequency is given, so that is not a correct answer. Next, the frequency of X-rays, gamma rays and UV rays are A, B, C respectively. Then, so frequency of X-ray, gamma ray and UV ray. So, if you remember the spectrum that I have drawn, first is gamma, next is X-ray, then we have UV ray, then we have visible, then we have infrared. Okay, by heart this spectrum. Okay, infrared, then we have microwave, and lastly we have radio waves. Okay, this has smaller wavelength, higher wavelength. Here we have highest frequency, here we have smallest frequency. Frequency symbol is given by this symbol. If you are not aware, this is called nu. Okay, this is the symbol for frequency. So the frequency of gamma ray, X-ray and UV ray. So gamma ray has highest frequency, right? So we can say that gamma and nu symbols are almost appearing same. So let me write gamma ray in capital gamma. So this is the symbol for capital gamma. Okay, so gamma ray have highest frequency. Okay, so X-ray, this is A is X-ray, A is X-ray, B is gamma ray and C is UV ray. Okay, so B must be greater than A and then both of them should be greater than C. So B must be greater than A and they should be greater than C. Okay, so remember this order. In terms of wavelength, gamma ray has smallest and UV radio waves have highest. In terms of frequency, gamma ray have highest frequency and radio wave has smallest frequency. Next question, the speed of light according to Maxwell's equation is given by C equals to 1 by square root of mu naught epsilon naught. So this is the expression for speed of light. The angle between electric field and magnetic field in an electromagnetic wave is 90 degrees. No other angle is possible. Okay, always electric field and magnetic field should always be normal to each other, that is perpendicular to each other. No other angle is possible for an electromagnetic wave. According to the generalized Ampere Maxwell law, so that's what I was talking about. According to generalized Ampere's Maxwell law, B dot dl equals to mu naught IC plus epsilon naught mu naught d phi E by dt. Okay, this question and the displacement current question came multiple times, so be careful, keep an eye on this type of question. Electromagnetic wave used in the treatment of cancer is you can mention X-ray, you can mention gamma ray also. So here X-ray is given, so you will tick at X-ray. Either X-ray or gamma ray, both are used in chemotherapy, if you have heard the term. That is basically treatment of cancer. Next, Which of the following ray is absorbed by the ozone layer? So ozone layer absorb X-ray, gamma ray, UV ray, everything is absorbed. Not only UV ray, they also absorb X-ray and gamma ray. All of the above is absorbed by the ozone layer. That's why it is very, very essential. Now, out of all the three rays, UV ray is most in terms of most amount, which is coming from the sun. Gamma ray and X-ray are less. Okay. Gamma ray and X-ray are less, but UV ray is one of the highest amount that is absorbed by the ozone layer. But X-ray and gamma ray, all high frequency lights are getting absorbed in our ozone layer. If there was no ozone layer, there would not be any life that could be possible on Earth. Okay, so ozone layer is the main protector, main shield that is protecting us from all the harmful rays. Which of the following ray is produced by hot objects? So hot objects produce infrared rays. Hot object produce infrared rays. So our body also emit infrared rays. So even if there is complete pitch dark, if you are wearing a infrared goggle, you will still be able to see me or anything, any object which is radiating heat. Our body is radiating heat, right? We are eating, we are digesting the food. Because of that, our body is radiating heat, producing heat, and that heat is being radiated by our body. So that's how the intelligence people, they monitor the terrorist activity, etc., the some unknown activity across the border. Okay, the armies and intelligence bureau, they monitor our border and any untoward incidents areas. They survey the area using infrared goggles. Okay. Which waves are used for mobile communication? So mobile communication use not X-ray, not UV ray, not microwave, but radio waves. Mobile communication happens mainly using radio waves. Which will produce electromagnetic wave? Accelerated charge, moving magnets, a static charge and a static magnet, a static charge. Only accelerated charge can produce electromagnetic waves. There is an alternative way, charge in a circular motion. Charge in a uniform circular motion. This can also produce electromagnetic wave, because a charge in a circular motion basically means accelerated charge. So accelerated charge will always produce electromagnetic waves. A circular motion means centripetal acceleration is always present, right? Circular motion. So if the electron is orbiting in a circle, it should always emit electromagnetic waves. The experimental demonstration of electromagnetic waves was done by Maxwell, Hertz, Marconi or Bell. It was done by Hertz. Okay, Hertz first showed the existence of electromagnetic wave, how perpendicular electric and magnetic field can produce electromagnetic wave, and in honor of his name, the frequency unit of SI unit of frequency was named Hertz. Okay, so if you see 50 Hertz, we are solving alternating current problems. So that Hertz and this Hertz are same. Okay. Next, write any two uses of ultraviolet radiations. UV radiations can be focused to very narrow beams for high precision applications such as LASIK. LASIK is the operation of your eye, okay, where your refractive powers can be corrected. UV lamps are used to kill germs in water purifiers or also in milk. Okay, so it is also used to sterilize milk. If you are using a UV at your home, we say RO UV, okay, UV RO. What is the meaning of UV RO? RO means reverse osmosis, which basically takes away all the hard materials that is present inside the hard metals which are present inside the water, so that water can be potable, that is drinkable. And secondly, they are passed through UV lamps so that all the germs are killed. Okay, bacteria and microbes that present inside the water, they are died. Then only that water is suitable for drinking. And same goes with milk. So milk is being sterilized by UV lamps. Similarly, the equipments used by a surgeon, okay, during a surgery, okay, all the instruments used by a surgeon during surgery are again sterilized by UV rays. So first, before the operation is conducted, the doctor uses UV sterilizer to sterilize all the instruments he is going to use or she is going to use during the operation. Next, name the electromagnetic waves used for the following applications: the radar system navigation used in aircraft navigation, the remote switches of household electronic system such as TV. So microwave is used for radar system and infrared rays are used in your TV remote. So if you see your TV remote, normally you will not see anything. There is still a LED light fixed in top of your remote control, but when you press it, you do not see anything because it's an infrared. Next time what you can do, when you are at home and you are using a mobile phone, switch on the camera of your mobile phone and switch on the video and turn on the your remote and you should see using the mobile camera. Then you will see that light is blinking because your mobile phone can detect infrared but our eyes cannot. Okay, very, very interesting. What is displacement current? Give expression for it. Displacement current is due to the changing electric field, is called current due to changing electric field is called displacement current, and its expression is given by ID equals to epsilon naught d phi E by dt. What are electromagnetic waves? How are they produced? Oscillating electric field in space which produces an oscillating magnetic field, which in turn is source of oscillating electric field, as so on. So this is how these are called electromagnetic wave. Electromagnetic waves are produced by accelerating charges or oscillating charges. Okay, this gives rise to electromagnetic waves. So what is the meaning of it? So when electric field is oscillating, okay, this electric field, changing electric field will produce a changing magnetic field. Okay, and this changing magnetic field will again produce a changing electric field. So electric and magnetic field, they carry on each other, and they start propagating. Okay, so that is why a changing electric field and changing magnetic field combined together can produce electromagnetic waves. Last question. Mention any two uses of infrared rays. Electromagnetic devices such as LEDs uses infrared are widely used in the remote switches of household electronic system such as TV sets. Infrared lamps are used in physical therapy. So physical therapy is where suppose you have a broken bone or dislocated bone and the doctor ordered you to go to a physical therapy, then the doctors uses infrared lamps to heat up the area. Is a very good heater, and that's how physical therapy is done, and infrared lamps are used over there. Infrared rays are also used in infrared goggles to detect human present or animal present when there is no light available. Okay, that is also an use. So this is the end of this lecture, but as I always say to you that don't forget to subscribe to our channel and share this video with your friends, and if you liked our channel and liked this video, don't forget to give it a thumbs up. I'll be back with a new chapter very soon. Till then, bye.